All right, good afternoon to you guys. Welcome to our lecture number 10 in our series in the study of Fourier series and also the complex analysis. This course has got two parts actually, but both are linked. Therefore, we have to do them in a certain order. Now, we've developed the mechanism to find the Fourier series. How do you write a function in terms of a series, infinite series of sines and cosines? We can do it for ordinary polynomials, but can we do it for sines and cosines? And the answer is yes. We dealt with the method. The method helps us to find the coefficients explicitly, ak and bk, and then you can write the series. Obviously, the question is, what's the use of all of this? Can it be used some way? It's interesting, but does it have a purpose? The answer is yes. In fact, that's how science goes. Mathematics develops because there's a need for something. And people are working with something and then they wonder, now, how can we do this? Then people go off on a tangent and solve that problem. So the mathematics and physics and applied mathematics all are interlinked. They drive each other forward. So today we'll be applying the work to, firstly, the heat equation. You may have come across the heat equation in Math 251, elementary equations, where let me just recap some work on differential equations. Recap. Because I will need this as we develop our work for today. So if you take a differential equation like, say, y double dash plus my equal to 0. Y is the function of, say, x. How does one solve the differential equation of that type? In other words, what function must y be such that if you differentiate it twice, add it to m times y, the answer will be 0. Those two will cancel out. Oh, I can even take a minus here. In fact, in the work that we're going to be doing today, let's put a minus here so that it's more convenient. Do you recall how this is done? Anyone? This is going to become the central player in most of the work to follow. You can do this with the Laplace transforms. Have you heard of the Laplace transform? Integral e to the minus blah 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 minus kt and stuff ds. Essentially, what you do is you write what we call an indicial equation. That's like a quadratic equation, like k squared minus m equal to 0. You solve that, you get k equals plus minus root m. And then the solution would be a e to the root mx plus b e to the minus root mx. Does it ring a bell? Okay, so that's the general solution of that equation. Note, however, if m is negative, say m is negative, so you'll have like the root of some minus number here, e to the root minus 3 or something. The square root of minus 3, that's where the I appears, isn't that so? The square root of a negative number is basically, so root of minus 3 is root 3i. So what happens, what's another way to express such a solution in that case? If you have e to the ix, e to the minus ix, what's another way to express that? Using Euler's theorem? Say it again. Cos and sine, that's right. You can express that as cos and sine. You can say y equals to a cos root mx plus b sine root mx. Okay, in the case that m is negative. In the case that m is positive, okay, let's take the case where m is 0. Now you'll see it will be e to the 0 is just 1. So you can get, in fact, it can just be x finally. I'm not worried so much about that. In fact, I'm not doing this in detail. I'm just giving you the flavor of this here. What happens if m is positive? Now you can leave it as it is because e to the root m is acceptable. Like root 3x and so on, it's fine. But recall e to the x plus e to the minus x over 2. What does that give you? What's another characterization of e to the x plus e to the minus x over 2? E to the x plus e to the minus x over 2. What's that? Cosh. That's cosh. So you can convert this to the shape y equals to a cosh root mx plus b sinh root mx. Right, so these are the different characterizations you can get depending on the value of m. M is 0, it will become constant, y equals to a plus b. Or you can even have an x there. You see, if m is 0, then your equation is y double dash equals to naught. Right? Because m here is 0. This is 0, y double dash is naught. Now that means that y, if you differentiate it once, y dash will be a constant. If you differentiate it twice, you'll get y equals to ax plus b. Some linear function. If you differentiate a linear function twice, you'll get 0. Okay? Right, so just remember this now. We're going to now introduce a heat equation, and this kind of knowledge is going to be important for us to go forward. So let's start off with the heat equation. The heat equation in the shape ut equals to alpha u xx, where u is a function of t and x, or x and t. So let's suppose the amount of heat, or the heat content of a certain object is given by the function u of xt. And the way this heat profile changes in this object is according to the law ut is always proportional to uxx. I don't know exactly how you get that equation. Engineers get these equations. Our job is to solve the equations. So, but if you want to go and see how they actually get this, it has to do with measurements and conjectures and stuff they make, where they claim that the change in the temperature, time-wise, is proportional to the second derivative of the space coordinate, x. That's the heat equation. You can have it in many dimensions. But in our case, we will study it in one dimensional, basically. So we'll have like a rod. Let's take a rod. We can approximate it by a one-dimensional object. Let's put this on an x, y, z system. Z. Let's say at x equals to naught, it is there, x equals to L. So the rod has length L. The temperature profile inside this rod is given by ut equals to alpha uxx. The name of the game is to find out what this function uxt is. Then when you find that function out, you will know exactly the temperature for a certain x value and for a certain time. So if you want to know what's the temperature inside this rod, let's say when x is 1 and the time equals to 10 minutes. So you plonk x equals to 1, t equals to 10 in the formula that we eventually get. That will give you the precise temperature at every point. Now, I'll bet you can't guess the function at the end. What kind of a function do you think u of xt will turn out to be? Unless you did this course before, in which case there's no fun. But if you're doing it for the first time, then you will never guess what the function is going to be at the end. It will certainly involve Fourier series. That's why we did the prelude already. But now, to solve a system of, or to solve a PDE, partial differential equation, which is what this is, you need what we call boundary conditions. So in this problem, let us assume certain boundary conditions, such as, let's say u at naught t is naught, and u of lt is also naught. So when x is 0 and x is L, temperature is 0. It's like immersing the rod in a bucket of ice on both sides. You keep the temperature at 0 degrees Celsius. The U is the temperature. So we are saying that at the two ends, the temperature is kept at 0 degrees Celsius. And then let's also give an initial condition. So there are two items here, boundary conditions and initial conditions. Initial is when time equal to 0. Let's say U at x0 is some function of x. So when the experiment starts, when you start heating the rod at the outset, at time equal to 0, you'll find that the temperature is given by some function of x. So if you want the temperature at x equal to 1, this function, let's say the function is x squared, then the temperature will be 1 squared, which is 1 degree Celsius. At x equal to 2, it will be 2 squared, 4 degrees Celsius, and so on. So the temperature at the outset, at the beginning of the experiment, is some function of x. I mean, we don't have to specify it at this stage. I'll show you in the end an example of it. So that's all you need. We now need to solve the system, or solve the differential equation, partial differential equation ut equals to alpha u xx, subject to these boundary conditions. Okay? Any questions so far about the model? That's a model. Find the temperature inside a rod of length L, given these boundary conditions. It's like taking a piece of wire and you place it outside in sunlight. The sun is shining upon it, it's heating it. So you're saying at the beginning, let's assume the two ends are, or not at the beginning, let's assume we put the two ends in a bucket of ice. That temperature is always 0 degrees Celsius. Let's also assume that at the beginning, at time equals to 0, the temperature at each point is some function of x, depending on what the x value is on the rod. Now let's heat it. So after 10 minutes, what is the temperature when x is 5 centimeters, for example? That's the question we're asking. You understand the question, the problem? Now we're going to crank it out. I mean, you really don't have to understand the logic behind it, but because now we're going to solve the mathematical problem. So the solution. So the equation is ut equals alpha uxx. Solving for uxt. Now, it's very hard to solve a partial differential equation, so sometimes we have to make some assumptions. So in this problem here, we're going to assume separability. Assume that the functions x, the x and t variables separate. In other words, let's say u is a function, some function of x multiplied by some function of t. X of x times t of t. That's a big assumption. We are seeking functions, a function of x and a function of t. You might be thinking, oh, this is cheating now. How can you say that? I mean, you're making it so easy. What if the function say sine x plus t? Can you split up that as a function of x times a function of t? Is there any way to split sine of x plus t? Like sine x times sine t, or sine x times cos t, or sine x times cos lim t, or something like that. Is it possible to split it up into two neat parts? One with the function of x only, times another with the function of t. You can't. Okay, if you take e to the x plus t, can you split that up? Can you separate that? E to the x plus t. Isn't it e to the x times e to the t? In that case, you can split it up. You can separate it. It's quite possible. But if it's sine x plus t, or lim x plus t, there's no mathematical way to split it up as a function of x times a function of t. You can't split it up. You can't separate them. So this is a bit of a leap of faith for now. Later on, I'll make a statement about this, and you'll see it's quite outstanding, or astounding, in fact, aside from outstanding. Let's assume separability. So that means that we are saying u is xt. So if I take ut, Now, the x part has only got x in it, so the partial derivative will be x times t dash. Dash will represent time. Dash is day t. If I take ux, this time the t will be a constant. You treat this as a constant. Remember, these are partial derivatives. When you do partials, you treat one as a constant and you work with the other ones. So this will be x dot t. This time dot represents day x. Partial derivative with respect to x. If I differentiate again, uxx, it will be x double dot t. Dot represents partial with respect to x. Dash represents partial with respect to t. At any time you're getting lost, stop me immediately. This is a very long story. The solution is long. So it doesn't help to come to the end and say, how did you get that dot? What's a dot? Right now you should clarify in your head. Right, so now we are on our way. The equation ut equals to alpha uxx becomes, so ut is xt dash equals to alpha uxx with x double dot t. I can cross multiply or cross divide and get x double dot over x equals to t dash over alpha t. Check that out. I take the x on the other side, I'll get x double dot over x. Bring the alpha t on this side, t dash over alpha t. I just rearrange it. It's the same thing. The beauty of that rearrangement is that now all the functions of x are on this side, all the functions of t are on that side. They separate neatly. So this side, functions of t of x, functions of x. And this side is functions of t. So I separated them neatly. So now you have to ask the question: if you got on the left-hand side just stuff with x in it, and you got on the right-hand side just stuff with t in it, how on earth can the two sides be equal? How can a function of x equal to the function of t? X sine x equals to ln t. Can't be possible. I mean, how can that be? There's only one time that can happen. When is that? There's only one way that a function of x can equal to a function of t. There's only one possibility. When? Which function of x is equal to another function of t? There's only one possibility. If both were constants. If f of x is 5 and g of t is 5, they can be equal. Isn't it so? There's actually no x and no t anyway, by the way. But that is a function. A function of y equals a 5. It's a straight line going through 5. So that's the only possibility. The only way a function of x can equal to a function of t is if both sides are constant. You're not believing this. Do you agree with this or not? The only way left-hand side can equal to right-hand side is if both are constant. Say lambda. I'm going to make an inspired use of the letter lambda. If you're not believing it, just raise your hands and ask, and I'll repeat it. I am claiming that the only way a function of x and a function of t could ever equal each other is if both are numbers. They are just numbers. They cannot have x in them or t in them. If they do, then they will never be equal. How can something with an x in it be equal to something with a t in it? It's impossible. The only possibility is that both are constant. So, therefore, now we have the following procedure. A, let's take x double dot over x equals to lambda. This implies x double dot equals to lambda x. Or I can say x double dot minus lambda x equal to 0. Hey, where did we see that before? X double dash minus lambda x equal to 0. Wasn't I speaking about it at the beginning of the lecture? Second order differential equation. Now it's an ordinary differential equation. It's no more a partial differential equation because there's only x in the problem. Capital X is a function of small x. There's no t. There's no more a partial differential equation. It's an ODE. So the solutions. There are three prospects. You can either have x being a cosh root lambda x plus b sinh root lambda x, provided lambda is positive. Or you could have ax plus b in the case that lambda is negative. Or the third prospect is you can have a cos root minus lambda x plus b sine root minus lambda x in the event that lambda is negative. So I discussed this at the beginning of the lecture, how to solve a differential equation in the second order. If I reduce it to an additional equation, then effectively you can get these three possibilities. And that's the solution so far. Now, just recap the boundary conditions. The boundary conditions, if you remember, it said u of naught t equals to naught. So this will mean that x of naught equals to naught. And of course, the other one was x of L equals to naught. U of L t is naught. So u x of L. Because the t part is independent. So let's now hit this solution with these boundary conditions. Let's see what happens. So we'll do it in three parts. Let's take A. Let's take the part lambda more than 0. So if we invoke x of naught equals to naught, plug in naught here. I'm changing x into naught. X of naught equals to naught. So it will be a cosh naught. A cosh naught plus b sinh naught equals to naught. Cosh naught is 1, so it's a plus b times, well, sinh naught is 0 equals to naught. And this means that a is naught. So a plus naught equals to naught, so a is naught. So with that boundary condition, the a becomes equal to 0. Now let's hit this with x of L equal to naught. I'm substituting here on top. Let me just refer you to with color. I'm substituting in the yellow stuff here, right? I'm substituting both these things in the yellow stuff there. So I firstly put the x equals 0, and then a times 1 plus b times 0 equals 0, which means that a is 0. That's the first conclusion. Now I'll plug in L. Remember, a is 0, so we only need to work with the other side. So you'll get b sinh root lambda L equal to 0. B sine root lambda L, it's not L, equal to 0. Now, what can you say now about B? Is B going to be 0? But can't sinh be 0? You can either have B being 0 or sinh being 0. Is it possible for hyperbolic sine to be 0? Does hyperbolic sine ever become 0? Think about the definition of sinh, e to the x minus e to the minus x over 2. It can't. So it's not possible for sinh to become 0. So this implies that B is 0. So B is 0. So this whole case falls away. So this case falls away. Right, now let's go to B. Let's take the case lambda equal to 0. Yeah? Yeah, L can't be 0 because there has to be some rod. The sinh L, yeah, okay, so you're saying the other possibility to make sinh be 0 is to have L being 0. But if you have L being 0, then you have no rod. Then we can go away because there's no problem to solve. So we can't have that. So then the prospects are that B has to be 0. So it turns out that the first option dies. Caution cinch is not possible. Now let's go to the second one. I'll repeat the experiment there. So let's take x of naught equal to naught. I'm now talking about the green one here, ax plus b. Let's plug in naught there, and we should get a times 0 plus b equal to 0. This means that what? B is 0. 0 plus b equal to 0, so b is 0. Then let's hit that with x of L equal to 0. Now b is 0, so a times L equal to 0. We just said L can't be 0, so what has to be 0? A has to be 0, so this also fails. Ooh, so far everything is failing. You're probably wondering whether this is ever going to work. We now come to the blue one. I think deep down, you know, there'll be a twist in the tail and the story will have a happy ending. It'll work. Well, let's see. So we are now taking the case lambda less than 0. So let's plug in x of naught equal to naught. This time we'll get a times cos of 0 plus b sine 0 equals to 0. In other words, a times 1 plus 0 equal to 0. Hey, a is 0. Doesn't look like this was going to work. Okay, let's now hit this with x of L equal to 0. So a is now 0. So we have b sine root minus lambda L equal to 0. Now, the question is, does that mean that b is forced to be 0? So there are two options. B can be 0 or sine can be 0. Can sine be 0? Can the sine of something be 0? Yeah. What is the angle? The sine of what is 0? 0, pi. Summarize that k pi, isn't it? Any k pi, any multiple of pi, sine is 0. So this does not imply b is 0, because b can be a number. So this can imply that root minus lambda L is some multiple of pi, k pi, because sine of k pi is 0. That is a distinct possibility. Or you can say root minus lambda is k pi over L. Or minus lambda is k squared pi squared over L squared. Or if you want to say lambda, then put the minus on the other side. K pi over L. That should be ringing a bell in your head. You can see where that is going. So, by the way, this lambda here is actually an eigenvalue. You heard of eigenvalue? Eigenvalue, when you have a matrix A times X equals to lambda X. When a matrix acts on a vector and the vector is scaled, that lambda is a scale factor, it's called an eigenvalue. The matrix that does the job, or the vector itself, is an eigenvector. And the solution set is the eigenspace. You've done this in maths what? 251? No? 212. Should have done linear algebra there. Eigenvectors, eigenvalues, and stuff. So it has the same kind of characteristic. So the lambda is an eigenvalue. So sometimes the solution space is called an eigenspace. You read in the notes, they use the phrase. All right. So to summarize this part here, we have found out that x is now given by, well, a was 0, so it's b sine, well, it's root minus lambda L, right? X. And we said that's root minus, so that's k pi, root of minus lambda. Okay, where was this thing? Look, have a look at the green thing here. A is b sine root minus lambda x. B sine root minus lambda x. Let's follow that there. That's the solution. B sine root minus lambda x, or we can write it as b sine root minus lambda is k pi over L, so k pi x of L. B sine k pi x of L. Oh, that should be taking some shape in your head. I've heard that somewhere before. Sine k pi x over L. Where did I hear that? Don't worry, it'll come back to you soon. So for now, we have found the solution for x. So just when you thought it was all over, now we go to t. This is only half of the problem. That's half we're finished. Remember there was t. T dash over alpha t equals to lambda. Remember we had x double dot over x equals to t dash over alpha t? And I said the only way those two could be the same is if both sides were a constant, say lambda. So we have dealt with the first one, x dot over x double dot over x. Now I'm dealing with the t part. So how do you solve this, guys? T dash over t equals to alpha lambda. How do you solve that? First order differential equation. You can just integrate, man. Integrate with respect to t. What is the integral of t dash over t? The integral, when you integrate and you have the derivative on top of the function, what's that? Come on, come on, come on. Ln t equals to alpha lambda t plus some constant. Let's call it c1. Okay? So I can say t is equal to e to the alpha lambda t plus c1, or e to the alpha lambda t times e to the c1. That's just a constant. So I can just say it's a constant times e to the alpha lambda t. And the lambda is the same lambda from above. It's a constant times e to the alpha. What was the lambda, by the way? It was minus k squared pi squared of L squared. There you go. It's here. Minus k squared pi squared of L squared. That same guy on the cushion in here. It's the same lambda. Both sides have to be equal to lambda. So this thing here takes on the more serious look. Constant times. Oh, I wrote that already. Constant times e to the minus alpha, so it's k squared pi squared over L squared t. Okay. So I now have u, which remember is x times t. X was b sine k pi x over L times t is e to the minus alpha k squared pi squared over L squared t. That's the x, and that's the t part. I've done both parts now. You may be wondering what happened to this constant guy here. Well, I just followed him up with b. B is a constant anyway. Actually, you can have many constants. There's a k in the form. What is k? K is 1, 2, 3, 4, 0, 1, 2, 3, 4, 5. You know what? So then, for each k, I can have a different b. So to conclude this here, I can put a bk here. B1, B2, B3. I mean, for each K. If K is 0, it's B0, blah, blah, blah. K is 1, B1. And I can take the most general combination of this, sigma. The most general combination of that from K equals to 0 up to infinity, and I've got every possible combination of sine and e to the minus whatever, which is the most general combination. And voila, I've actually solved the problem. I've got the temperature. I have now found out that the temperature profile is given by this function here. U is equal to that. Well, it's not really over. You thought it was over like about 10 minutes ago. The cat is on, rambling on and on. It's not over. There's still one more thing to do here. VK, you don't know what VK is. You have to work out VK. You have to work out VK, then it will be over. It's never quite over until the horizontally challenged lady sings, as they say. So now it remains to find VK. So if you go back to the game, you'll see that we have used the boundary conditions, but we have not used the initial condition. We have not used it yet. That's where it comes into the picture. We now invoke the initial condition. We call this result 1. The initial condition was u of x0, some function of x. Only 0 temperature depends on the position on the rod. It will have a certain value, and that will be the temperature at time equals 0. So plug this in, plug in 1. So we'll get u of x0 equals to sigma bk sine k pi x over L. There's no t there yet, times e to the power, now t is 0. Initial condition, t is 0. Put the t is 0 here. Yeah. E to the 0. What happens there? E to the 0 is 1. So this collapses to bk sine k pi x over L. K equals to 0 to infinity. And this is supposed to equal f of x. So f of x is sigma bk sine k pi x over L, and k is 0 to infinity. Doesn't this resemble your Fourier series? That is the Fourier series. So all we need to do to find out bk is like the small bk we had before. So we put bk equals to bk equals to 2 over L integral f of x sine k pi x over L dx from 0 to L. It's like the odd extension. Because it's a sine problem, because this problem has got sine in it, because the problem has got sine k pi x over L, we choose the odd extension. So we go with 2 over L. Instead of minus L to plus L. Remember, with the odd extension, you add a small tail on the negative side. And then, because it's now a symmetric function, you have 2 over L. So if you solve this, if you find this here, then the problem is over. So for example, let's take an example. Say f of x equals to 1 degree Celsius. Say everywhere the rod is 1 degree Celsius at the beginning. So the bk will be 2 over L integral of 1 sine k pi x over L from 0 to L. Integrate that, that's 2 over L. Integral of sine is minus cos k pi x over L over k pi over L from 0 to L. Oh, sorry, that is moved away. Right, I just need to finish this off here. This becomes 2 over L times L over k pi. Of course, let's pull the minus out there. Then we substitute L in cos k pi x over L. It becomes cos k pi minus cos of 0, which is 1. So we end up getting, well, the L's cancel off, minus 2 over k pi into minus 1 to the k minus 1. If k equals to even, bk is 0. If k equals to odd, then bk is equal to minus 2 times minus 2, which is 4 over k pi. So we can say bk equals to small bk equals to 4 over k pi. Hence, in conclusion, and this is the conclusion, uxt is sigma bk, which is 4 over k pi, sine k pi x over L, e to the minus alpha k squared pi squared over L squared t, and k equals to odd. So if you expand the series, that will give you the temperature profile inside the rod after time equals to 20 seconds and for a certain x value. You never thought. Would you have guessed that's the temperature profile at the beginning? Hardly. These are quite significant. In fact, for now it's a short rod, but in the third chapter, the rod will become an infinite length rod. And it's like infinite length means like a long wire, like a telephone wire. So if you have a telephone wire sitting in the sun every day, or electricity cable, it's subject to the sun's temperature changes. It gets heated up. So how does the temperature affect the strength of it and the transmission of the signal? All these things are important to engineers. That's why you need to model this in this way. All right, we shall stop there. Any questions?